Thank you so much for having me. So I'm going to talk today about recent research and directions, interdisciplinary collaborations, thinking about how we can overcome the autonomy paradox with generative AI. And this might be a little hard to read, but I'm sure resonates. So in this little comic, he says, I wrote some software that automates one of my mundane and repetitive tasks. She says, careful, the automation paradox states that the more we automate easy tasks, the more we're left with difficult tasks of dealing with the system when it goes awry. So he says, I already thought of that and wrote a function that handles any faults and another one that just watches that one. I've thought of everything. It's foolproof. And then she says, so what will you do with all of your extra free time? Hold that thought, I'm getting a compiling error. So this is like many of our lived experience, and it's kind of funny, except that it's not. So what I want to do is start by talking about the historical precedents for the autonomy paradox, and talk about the ways in which we can think about generative AI helping us overcome these challenges. So I'll start with a look back in time to the year 1982. And this is a New York Times clipping from about 1984 when GM announced a factory of the future in Saginaw, Michigan. So the idea was that they were going to use robots to automate lights-out manufacturing, essentially meaning there'd be no people. You could entirely turn out the lights and everything would just run just fine because robots don't need lights. So things didn't turn out as expected. The robots actually placed Buick bumpers on Cadillacs and vice versa. The robots actually spray painted each other rather than the cars, which sounds funny, but it was a unmitigated disaster. So the entire project was abandoned. And I've talked about this a few times at MIT, and in some of the circles I talk about it at MIT. One of the senior people at MIT said, I actually had a startup that was helping develop the scheduling software for this factory. We were the only technology provider embedded in this project that didn't go belly up as a result of sort of engagement in this project. So 1982 to 84. Let's jump forward 20 years now to 2002. So, arguably technology has advanced in leaps and bounds in those 20 years. And at that time, 2002, the Navy unveiled their plans for what's called the Littoral Combat Ship, which was meant to be a highly autonomous and intelligent naval vessel that would operate with many fewer sailors. So unfortunately, that dream fell apart as well, kind of billions of dollars later. And this is a news article from recent times doing a retrospective of the last 20 years, talking about how these still exist in different form than they were originally envisioned, but they're kind of on track to meet their original requirements. So the LCS, it was initially intended to be operated by 45 sailors, and it actually ended up requiring more. It required 60 sailors. Those sailors needed higher skills, sort of a higher grade, and as a result of that, a higher pay grade than those typically required for traditional ships. The cognitive load associated with working on these ships was much higher than a traditional ship, leading to sort of burnout and turnover issues. And in fact, there was also evidence of sort of negative training transfer. So sailors that worked on a traditional ship and then had to train up on working on the LCS actually performed worse on the traditional ship when they went back to the traditional ship. And this highlights the human systems integration, the human factors challenges that arise as we're trying to introduce new technologies. So these are famous examples of what's called the autonomy paradox, which is that as we introduce automation, it doesn't eliminate the need for humans, but instead it changes their role. This is what my colleague Ben Armstrong and I at MIT call zero-sum automation. And the challenge is that many companies sort of look at the business case for introduction of these technologies in terms of a labor displacement calculation. They're looking at how these technologies can reduce kind of headcount and directly measuring the success of the technology by the cost and output of machines against the cost and output of human workers. So the problem is that this approach limits flexibility, as we see in these kind of historical examples, meaning that it makes it harder to adjust to changing requirements and objectives. And it also underestimates the true value that humans bring and overlooks the ultimate broader potential for automation. And very unfortunately, this problem actually follows us into present day. I do a fair amount of work in manufacturing, robotics, and collaborative robots for manufacturing. And I was astonished to learn around 2018 through interdisciplinary collaboration with my colleagues at MIT that this conception of robots taking our jobs as we introduce more robots into factories, how do we address the sort of societal and worker implications for this? Well, I would just ask you, what % of factories today would you guess has a single robot? Throw out a number. 80%. 80% has a single robot. Other ideas? 5%. All right, the truth is between those two. It's actually 10% of manufacturers have a single robot, and most are low users of that robot. So the large firms like automotive, there's a few industries that utilize robots at a high level, but the vast majority can't find a use for even a single robot. And a problem is a part of this is the time, effort, and resources necessary to set up and program these systems, the changeover cost. Many companies don't have internal expertise to be able to even program these systems. And so it's really only the large companies with high rates that can kind of make the business case for it. Small and medium manufacturers, which represent 98% of manufacturers in the US, lag very far behind. So I want to talk a little bit about how we can avoid this trap and how we can sort of achieve the best of both. How do we achieve productivity, a positive business case for firms, as well as increase the quality and availability of work for workers. And it requires that we designing a human out, it requires that we think about how we design humans and automation together to increase these goals, to increase productivity, to increase flexibility. And so it requires different approaches to technology development, and we more broadly have worked on this for a long while. But what I also hope as a takeaway from this morning is that it also requires more than that. It requires designing for skills and training, and it requires rethinking about how we make the business case for technology. And as we pursue those goals, that actually changes the technology requirements for us as we're sort of doing what we do. So the question today is, as we look towards generative AI and the ways that it is and can potentially transform work, the question is, to what extent can generative AI increase flexibility of these technologies and allow us to overcome the autonomy paradox? So before I get into addressing this question, I want to further complicate the question a bit. And that's because flexibility, meaning the system to adapt to changing requirements, to work effectively with people according to human needs, is not actually our only goal here. AI is being increasingly deployed in high-stakes environments, and we're grappling with the new challenges and new regulation, for example, in AI in healthcare. And AI is even being deployed as a part of the US services. For example, autonomous aircraft are teaming with piloted aircraft in combat settings. And I have at the bottom here a quote from actually a stated requirement from the DoD for the Air Force autonomy program, which is that AI be implemented in a way that enables, quote unquote, appropriate levels of human judgment and oversight. So the question is, how do we know if we succeeded in enabling appropriate levels of human judgment? How is that measured, and what does it mean? And we know from the implementation of prior forms of automation that the use of automation can result in serious negative consequences. This is for sure an example today. It's a challenge that's posed by deep and highly parameterized AI models. But the references and sort of the insights I'm pulling here actually are very well studied and well characterized for traditional forms of automation, never mind AI. And that's that automation can undermine an operator's ability to identify a problem and appropriately intervene. And humans, even well-trained experts like pilots, can easily become complacent in the technology and overtrust it. It can undermine a person's understanding of their progress through a task or their understanding of the environment, in other words, their situational awareness. And automation can even degrade manual skills. So this is why to kind of quote-unquote remain current, pilots must themselves perform a certain number of takeoffs and landings a month, not using automation. So even with traditional, more transparent, arguably, forms of automation, it's actually very difficult to get this right out of the gate. So I'm pulling here the data from Airbus of the average fatal accident rate by Airbus aircraft generation. And what we can see from this data is that each new generation of aircraft comes with challenges. For example, among the technologies, among the upgrades, it includes cockpit automation, which is intended to make aircraft safer. But we see that the accident rate spikes while the human systems integration issues are being worked out. But we can also see that if we push past these spikes and implement best practices for human automation interaction, it has actually, the introduction of these new technologies helped us to achieve the current day unprecedented safety level for commercial aviation. So the question is, what are these best practices, and how do they relate to generative AI so that we can potentially avoid these spikes and see the benefits of the introduction of this technology? How do we achieve what is the equivalent of today's unprecedented success? And how do we avoid these situations where things really go terribly wrong? So one concept from human factors that's particularly relevant to AI is the concept of situational awareness. It's been applied widely in aviation in addressing pilots' informational needs, as well as other high workload, high stakes settings, autonomous driving, medical care, military operations, search and rescue. And it's been shown to correlate with team performance across all these domains. And a core finding is that situational awareness, or actually the loss of situational awareness while operating these highly autonomous systems, has accounted for deaths in hundreds of commercial and general aviation contexts, as well as other areas, other domains. An essay is defined as the ability to perceive, comprehend, and project the state of the environment. And so the goal here is how we uphold a person's situational awareness to be able to effectively take control or cede back decision-making authority from an autonomous machine in the event that that machine fails. And when a person doesn't know what a machine is doing and is undermined in taking back that authority, we call it kind of automation surprise. So the concept of situational awareness has been formulated as a 3-level definition, including level 1 is perception, upholding a person's perception of elements in the environment within a task-relevant volume of time and space, being able to take those attributes or features and make meaning of them, to be able to comprehend them. And then the 3rd level is to be able to project their status into the near future. So looking at this sort of very concretely, for a pilot might have a question as to whether they have enough fuel to get to a destination. They would look at the current fuel level as level 1 input, but level 2 need to comprehend what this means in terms of the possible range of the aircraft, how much further they can fly with that amount of fuel. And then at level 3, they need to be able to project whether they'll reach their destination before fuel runs out. So this is a simple example for a singular task, but a person's overall situational awareness includes all of the information that they need for their given tasks. It includes the environment, human teammates, their task, its status, and importantly, it also includes information about any autonomous teammates or AI or automated systems that they're working with. A pilot actually equally needs to train with the autopilot and the flight management system, as well as the other pilots in the cockpit. So focusing on this aspect of SA as a launching point, so we've developed the Situational Awareness Framework for Explainable AI, SAFE AI. And this framework allows us to systematically determine the information an AI system needs in order to be able to explain itself in support of humans in performing their tasks. So SAFE AI, like the SA framework, is a 3-level framework. And we can look at XAI, Explainable AI, for the first level, for perception, defined as explanations of what an AI system did or is doing and the decisions made by that system. So level 1 explanations are aiming to answer the what questions and typically give information about the system's inputs and outputs. Level 2 for comprehension refers to explanations of why an AI system acted in a certain way or made a particular decision. and what that means in terms of the system's goals. So level 2 explanations are answering why or how questions, and they're typically giving information regarding the system's model or internal decision-making processes. And this is where you would also see information about causality in AI systems. And then level 3 is XAI for projection. And this includes explanations of what the AI system will do next, what it would do in a similar scenario, what would be required for an alternative outcome. So level 3 explanations are answering the what-if questions, and they're typically incorporating counterfactual or other simulated information to provide details about the future system's behavior and what happens in regard to changes to inputs, outputs, or models. So one thing to note here is that application of this framework is highly context-dependent, and it's context-dependent related to the task, related to the human's role, related to the human or person's expertise, as well as other factors. So when we look to apply this, we're asking questions from the perspective of different stakeholders, and it enables us to be able to account for the needs of these different stakeholders. So given the insight that essay regarding AI is critically effective to our implementation of automation in AI, I want to refine our question here, which is, to what extent or how is generative AI a way in which we can increase flexibility of the technologies that we're working with and transparency? How can we achieve both these goals to be able to overcome the autonomy paradox? And thought of another way, can generative AI help us leapfrog past the challenges of these previous forms of automation? In particular, the need for specialized expertise, time, and resources to implement in ways that we see are relatively inflexible and result in these integration challenges. And can we do that in a way that's also transparent, that can support human situational awareness? So what I'm going to do next is use robotics as an illustrative example to start to look at this question, because I run a robotics lab, and it's a very visual way of working through this. So as I'm sure you're all very familiar now, I'm pulling some videos here from the Code as Policies work from last year. And I want to talk a little bit about how LLM-based solutions, to what extent, as we look at implementing them, they serve to replace or displace human judgment and expertise or not, and are flexible and transparent or not. So we know in this work that these methods are essentially working with a set of predefined skills and APIs and combining those skills to solve tasks, but with very, very impressive results, right? Very, very flexible seeming behavior. Place the blocks in the bowls with non-matching colors, put the blocks in the vertical line below the blue bowl. And so in these types of works, the methods are assuming primitives that an LM can sequence to solve these multi-step tasks. But the question is, where do these skills come from? The grounding here is happening at the skills level, and one of the challenges is that it can be too coarse to adapt to perturbations in the environment, meaning sort of, at the skill level, somewhat inflexible when things go wrong. We also have questions about the grounding of the LLM's interpretation. So in one of these, please place the block in the sky-colored bin. What is that grounded to? Or put the apples and the Coke in the corresponding bins. Who decides what bins? What if it's wrong? And so, in this sense, we don't have insight into the features or model details or what-if scenarios that we know we need to support human situational awareness to integrate this in a higher stakes environment. So, in some sense, at that perturbation level, not as flexible as we would like, and challenges around supporting transparency. On the flip side, we can look at other very exciting developments in teleoperation and imitation learning with very complex humanoids and low-cost robots that are doing very challenging tasks. So you might have seen Optimus folding clothes, or the very impressive sort of Aloha system out from Stanford. And these are very impressive sort of imitation systems for multi-step, long horizon tasks. However, these are taking sort of continuous trajectories and imitating the task. And you can imagine, what can and does go wrong from the blooper reels that we all have in robotics labs of a system that is blindly imitating motion without developing kind of a deeper understanding of what success means for that task. So in this case, when something in the execution is a bit off due to internal errors or changes in the environment, the robot pours the liquid on the table instead of the bowl. So in one sense, these systems are kind of like transparent in that they're really aiming to imitate what a human is doing. We can talk about whether that corresponds to the 3 levels of XAI or not, but there's a sense that the capabilities are transparent, but we still sort of lack in flexibility. And it's these sort of challenges that make or break these implementations and that sort of kind of result in this autonomy paradox. So what I want to do next is talk a little bit about why these errors arise. It's because when we provide a continuous demonstration to the robot, there's so much, as we know, there's so much more embedded in that demonstration that we require to make explicit for success. So the human demonstrations look like reach the white bowl while keeping the pan in the hand. If the pan is above the bowl, pour. Embedded in this are constraints and preconditions, and the sort of continuous trajectory often makes these sort of implicit. But they're very important to make explicit as a part of the learning process, both for increased flexibility and transparency. So what I want to do next is talk about an alternate way of thinking about how we can architect generative AI into these systems that supports a human-in-a-loop approach and that adheres to the safe AI framework and provides a path forward to potentially delivering both on increased flexibility and transparency. So the key idea here is to leverage LLMs in very specific ways to be able to fill in the gaps of these human demonstrations. And I'll show that how we can achieve advances in flexibility, transparency according to the safe AI design guidance, and as a direction I'm quite excited about. So what I'm showing you here is a robot doing pick and place via imitation, but without the LLM-based replanning that I'll share. And you can see that there's missteps. It goes to pick up the block, sort of doesn't realize it hasn't succeeded, continues on in the task. Then with imitation, with strategic use of LLMs as part of the replanning process, we see much more robust behavior in that pick and place. And so the goal here is to be able to, much like the prior systems, teleoperate through the robot morphology, gather the demonstrations, and develop an imitation policy. But to do so and work with that policy in a way such that it can afford close proximity human-robot interaction, supporting integration challenges. And here I'll talk specifically about what that means in terms of being robust to physical perturbations of the system at its execution. So in sort of task and motion planning, the challenge is that not all perturbations are created equal. So the same type of perturbation at different steps in the process has very different implications. So if we provide a demonstration via kinesthetic teaching here, and we want to learn a reactive motion policy using existing techniques, we can see that when we perturb that task replay before it scoops the marbles, it's fine and it continues on. It's robust to these sort of motion-level perturbations, as the motion policies are designed to be. But if we conduct a sort of similar perturbation at the next step in the phase, we've actually introduced a task-level perturbation here. It's dropped the marbles, but with the policy, it's going to continue on and try to drop the marbles, even though it no longer has any marbles in its spoon. This is a very interesting multi-step task with different geometric constraints and contact constraints that need to be maintained through the different steps. And so underlying this is that the task success depends on working through multiple modes as demonstrated. So you can see this sort of 2D abstraction of the 3 manipulation modes, a reach mode, a scoop mode, and a transport mode. And if we perturb that empty spoon at the beginning, it's fine. The robot can continue on. But if we perturb it at a different point, it's going to drop the marbles, and actually we don't achieve the task in the end if it continues on to the attractor or to the goal. And so what we need instead is the ability to be able to sort of replan at that step and know when we need to replan in that multi-step task. And so the goal here is to be able to take unsegmented successful demonstrations and address the fact that behavioral cloning techniques lack a replanable discrete abstraction. But we want and need those discrete mode abstractions. So how can we use LLMs to be able to leverage with lower human burden the development of those discrete abstractions? And also, how can we move away from sort of the need to hand-design pre-built sensors for every step along the way? We can see that we have various sensors that need to be defined regarding to contact during scoop, regarding whether marbles are in the scoop, regarding keeping the spoon level during transport. LLMs don't quite get us there on their own. As I mentioned, we have to work with pre-built skills and do the checking of feasibility and sequencing those skills. So the fundamental challenge is that these LLMs lack physical grounding. And so the question is, how can we bridge that gap? And how can we, in this case, learn classifiers to ground language in the demos that can overcome these challenges and allow us to reap the benefits of leveraging LLMs as a part of this process? So what we do is we leverage the language plan. We leverage LLMs to produce a language plan of the mode sequence. For example, we can prompt the steps for scooping and dropping the marbles into reach, scoop, and transport. We take our unsegmented demonstrations, and our aim is to learn classifiers to classify sort of each state in that trajectory space with regard to discrete abstractions of those modes. And each mode is representative of an execution policy, or you can also think of it as a skill. And then to leverage the LLM to replan at the task level, so to understand the transition constraints, the logical transition constraints associated with that task. And I'm showing you here a video of reach and scoop where the system has learned the classifier through this process as to whether marbles are in the spoon. And how that can be, well, I'm going to show how that can be leveraged to initiate replanning at the task level. And towards reducing the burden of integration, we want to move away from a process in which we densely annotate these modes and in which we ask people to demonstrate failures, which can be hard and dangerous, and instead use a paradigm of replay of the human demos and then artificial perturbations with a sparse signal of task success at the end. So what this looks like is we take a few successful demonstrations. Here's an abstracted task. We're aiming to teach the robot it has to move through modes green, blue, yellow, red. So we give a few demonstrations of successful executions from a variety of different angles. And so that's the demonstrated sequence. And we can also note that we have invalid mode transitions here. So if it pops out of one of those colors, we want it to always go back to green and restart its trajectory. And so our goal is to add perturbations to these successful examples and score at the end whether the task was successful or not, so a sparse reward. And you can see the process here of the robot sort of injecting perturbations to use in its learning through counterfactual reasoning. And so the assumptions here are that we're replaying and resetting to allow the robot to collect a lot of data on its own, adding these perturbations, and then labeling the executions at the end. And ultimately, the question is, well, what makes a continuous policy rollout successful? All the transitions are valid, or it's a failure if at least one transition is invalid. And this is one of the ways where we leverage the LLM to sort of prompt this feasibility matrix of mode transitions as use in this pipeline. And so you can see here that the one transition from reach to drop off is invalid. It's a -1 if it does not successfully sort of scooped the marbles. And what we do is we take the data from these demonstrations and perturbations, and as I mentioned, we train a classifier that computes the per-step feasibility. And then from there, through a differential calculation, the trajectory feasibility. and then ultimately scores the success of those labels. And the differentiable calculation supports backpropagation for training those classifiers. And so this works excitingly well. So we can see here from all these random perturbations of the robot moving through this abstracted 2D environment, we can learn the state-based classifier. We can learn image-based classifiers directly from the image, and be able to take any state and sort of score the ground truth. So in this case, it's wrong. It's in the yellow area, but it's inferring it's in the sort of blue mode. The ground truth is yellow. But in other cases, it does successfully classify what mode it's in, its end effector is in. And so the sort of outcome of this is the robot learning this classifier for whether it has the marbles and how to use that information. We can see here it dropped the marbles. It has no marble. So this is what you get with sort of model-agnostic behavioral cloning. It's not recovering from the task-level perturbations. And then this is what you get with this sort of glide approach. The robot has detected no marble, goes back, re-scoops, detects marble, many perturbations, and then successfully drops the marbles into the bowl. And this is enabled by learning the grounding, leveraging the LLMs, and also employing the LLMs to sort of guide this replanning process. So zooming out a little bit to a slightly more complex domain, we actually integrate LLMs at 3 levels. One is in a more complex or pick-and-place domain, use a visual language model to have it propose features in sort of this feature space to use as a part of learning the classifiers, and then down-select that with a prompt related to the task description. And that becomes the feature space that's utilized for training the classifier. We prompt the LLM to propose feasibility of mode transitions for the task and abstractions that are meaningful to humans, where the output, again, is this both human and machine interpretable sort of matrix structure. And then third, we leverage this pipeline to do these sort of what-if perturbations and sort of counterfactual updates. And so these 3 ways, they're not end-to-end, right? They're very targeted in how we're leveraging LLMs to a human interpretable, understandable, and modifiable structure as a part of this pipeline is purposeful. And each of those 3 uses of the LLM actually corresponds to these 3 levels of the safe AI framework. So at level 1, we're leveraging the LLMs to produce human interpretable and inspectable structures regarding what it should perceive to use as a part of this training process. At level 2, we're using the LLM to propose the feasibility matrix of transitions, which is sort of comprehension, making meaning of how those modes need to relate in order to succeed in performing the task. And then level 3 is leveraging these counterfactual perturbations to utilize sort of the what-if scenarios to build a representation that can be used as a part of trusted planning and control methods to produce reliable and trusted system behavior. And so this is towards using LLMs to sort of fill in these gaps in human demonstration. And we can see that it provides much more flexibility with regard to traditional behavior cloning and sort of response to errors and perturbations from people and in the environment. And it moves us towards being able to support appropriate levels of human judgment by providing outputs that are directly inspectable and usable as a part of a trusted system pipeline. So this is very early work in our lab. But in terms of coming back to the question for generative AI, to what extent can generative AI help us increase flexibility and transparency to overcome the autonomy paradox? I'm very excited about the possibility. Currently, the technology is not being used in many high-stakes environments, but with sort of a systems orientation of understanding the ways that it can sort of unlock additional flexibility and using it in a way that provides appropriate oversight, I think that there's exciting possibilities here. I'm less personally excited and optimistic about sort of end-to-end, but it doesn't, but pushing, to the extent that we can use those technologies is very important from sort of a research perspective. So what I want to do now is maybe just make kind of 2 more points that I think are important to make. I focused in this talk about really narrowly about ways we can use technology to sort of overcome the challenges we faced in automation and AI in the past. I also sort of engage at MIT in a wider interdisciplinary research group and community of study around work of the future and ways that new technologies can lead to better work and quality work for workers. And it's been very valuable for me to understand how we think we can sort of make a change with regard to new capability and technology, and that's going to unlock a world. Back to the discussion about industrial robots, only 1 in 10 manufacturers have a single robot, yet the robot manufacturers are puzzled by this, because by their analysis and other analyses, standard industrial robots, never mind anything with generative AI, standard industrial robots without even much external sensing should be able to do like 90% of work in most of these factories, and they're not being utilized. And so it's a skills and training problem. It's sort of a business models problem. And I'm very fortunate to collaborate both with social scientists and faculty from the Sloan School of Management at MIT to be able to better understand these other factors. And as I said, it sort of informs how we think about driving our research in the lab. And just to drive this point home, I'm going to talk very briefly and show you a short video on manufacturing. This is sort of a video documentary of one of the small manufacturing firms based in Ohio, G&T, that totally bizarrely has like cracked the nut and is scaling their use of automation and is hiring. They have higher quality jobs. They see like this flywheel of success that is the dream for everyone else, using just off-the-shelf standard commercial technology. And so it's in case study, it's very important for us to understand how and why they were successful at this and how this can be replicated elsewhere.
Now turn the robot on. I mean, these are new, but if you ever watched the original Terminator movie, at the end they're using machines like this. It's for loading and unloading the parts. It saves us a lot of time.
Everybody sees a robot roll out on the floor, and the first thing everybody thinks of on the shop floor is, well, that's it, they're gonna cut the workforce. But someone still has to monitor, someone has to tend, someone has to set up, someone has to change over that robot. So you still need that skill set, you still need a person.
When you're in a small shop, you got a lot of different things to do. This allows me to run the robot down there, I hand that one, and I do the inspection too.
When they're new here, they're like, oh, I can unload and load that machine faster. I'm like, yeah, but you can't unload and load that machine faster 24 hours. You can't do it for 48 hours, and you can't do it for 7 days and work every single hour. So by getting the people trained in the technology like this, you can become very competitive on the global stage. Not 5%. G&T Manufacturing was started in the late 70s by my grandfather and my father, Gerald and Tom.
Your grandfather?
They came over from England.
That's myself.
They built it from having just a few customers.
Where did Mum find these at?
To where we are now, manufacturing parts, whether it's for the aerospace industry, food industry, lift truck and heavy industries, and all those items that fit in there in agriculture. And we compete in that global marketplace with robotics, automation, and trying to keep up with the latest technology trend.
See it changing? Yeah. So it's going to change.
Before we got this, I used to load them by hand, and it was, I believe, faster. Just kidding. But it actually loads it better. When you're loading a part, I'm holding it like this. I'm not getting equal force on it. It's just my muscles, so each time it's different. You'll get different sizes and you're not going to get that clean surface. So this will do it all for me, saves me a little work, saves the back.
Our first push into the robotics for the heavy lifting was a safety concern for our workforce. And then once we did that, our ROI on the first robot we bought for heavy lifting, we had the ROI of $140,000 investment. It took us 3 months because our efficiency went so high on day shift that when we ran it on night shift, we actually gained all that time back, and we actually got so far ahead, we had that many of those parts through the lathe that we could no longer support it with our other processes in the shop. So we had to relook at all the other processes in the shop.
We are so busy. A lot of this is we have another warehouse, but this is jobs I got to check in, just raw material. So we've been speeding. We got another machine coming to town, so that'll be interesting.
So anybody can go out, purchase exactly what we have. There's no real magic to what we do per se with the equipment. The more of the magic is the culture and the workforce of getting them to accept the value of the automation.
I'm 60. As for a computer, I don't own one. I don't deal with one. So it's not that hard.
The way we had it set up was we had a bonus system that was in place. You just got to hit 80%. Well, there's no way the robot's going to duck down under 90, so these guys are hitting these 10%, so they're hitting these huge bonus markets, and that's what really made it easy to get the robots and automation on our shop floor. Was everybody wanted to run the automation. Everybody wanted to learn the automation then. Worrying about all of a sudden the door opens up, boring about there. We believe in the all ships must rise mentality. So if you don't backfill in the community and develop them into these higher technology, machining and manufacturing jobs, you have nothing to pull from. So it seems like it's a fairy tale, but then you realize all of a sudden you are actually living in that fairy tale because the production from the automation is actually carrying your shop, and all of a sudden you realize you have a happier workforce and you're making more parts, so you have a bigger ROI, which then allows you to actually pay all of your workers more money because you actually become more profitable because you become more efficient. So if everybody's happy, then we all gain, and then all ships will rise.
So this is like an incredibly inspiring and exciting story example, and I can't stress to you again how rare this is. This is the success story that everybody's striving for, being able to upgrade technology, increase competitiveness, increase productivity. GNT then also grew to offer more and better quality jobs. And the culture, the skills and training, the incentives aspect of this, all of this is really kind of, you could see, diametrically opposed to the conception of a lights out factory and removing a person from the process, that sort of displacement mentality. And actually the Air Force is studying. Colin is now quite famous based on the work we've done to elevate this story, which is great to see. Our work continues on. So we also see that generative AI will require a nuanced, equally nuanced approach that takes into account the interplay between technology, human workers, and organizational contexts. We have a large working group at MIT, which I co-lead with the social scientist Dr. Ben Armstrong and Professor Kate Kellogg from our Sloan School of Management, working with more than 40 companies as they're sharing with us their scaling, use case, and sort of business aspects of their increasing use of generative AI. And I think what's both exciting and also, in my view, somewhat concerning is that generative AI is not immune to all of the challenges that we've seen. It's not sort of a silver bullet that will supplant and fully replace human work. We don't see evidence yet of wide-scale displacement through the introduction of new technologies. But we do see the ways in which companies that have made long investments in AI and data infrastructure are very strategically, like I sort of described we're doing in robotics, leveraging the technology to unlock a pain point they had in a pipeline that is transformative. So very interesting uses in AR, in HR, in hospitals with ambient note-taking. The medical field seems to be on the forefront in innovative and successful uses of these technologies on the business side. And then also very, very interesting scholarship highlighting, again, the human factors and systems integration issues of these technologies. In an experiment with BCG, Kate Kellogg co-led a study of 758 consultants, giving them generative AI for 2 tasks, one a creative task, which generative AI is sort of well-suited to support, and another one that required analytical problem solving. Those that used the technology for creative tasks saw a 40% boost in performance, but those that used it for the analytical task, which it was poorly suited to, were 19% less likely to arrive at the correct solution compared to those that were working with it. So big pros, big cons, and what's called the jagged frontier is very hard to characterize right now, where it's suitable and where it's not in support of human work. We see very interesting takeaways of firms and how they're deploying this technology related to the benefit of prior investment in AI and data infrastructure, and related to the benefit of very agile, experiment-driven approaches that work very closely with workers to understand and collect data to understand where we're within the frontier of its supporting work and where it's still outside the frontier. And so this is the working group, the Work of the Future initiative at MIT. And for those that are interested in this, please do reach out, get on our mailing list, newsletters, and we'd love to have you involved. And with that, I can wrap up and take any questions. Thanks so much.